8 years ago, a younger version of me sat down and flipped a coin 10,000 times. If you're wondering, why would anyone do that? Look, we don't welcome those sorts of questions around here, but more to the point, I wanted to see how often it would land on its edge. And later on, I'll explain why I was doing that, how many times it landed on its edge, if you want to. See if you can have a guess. 10,000 flips, how many edges, and I have a ridiculous joke collaboration we shot, which has never seen the light of day. That'll be right at the end of the video. See if you can guess who else is involved. But for now, we're going to speed forward 8 years to when these flips finally became useful. And it's because of Pi Day. Yes, a few years ago, I flipped a coin 10,000 times. I don't know what I was thinking, but I've finally come up with a use for that footage. I'm going to use it this Pi Day. So hey, happy Pi Day 2026. Although, shouldn't have said that. Forget it's Pi Day. Spoiler. This is not a video about that. This is a video about flipping a coin a coin to see what the ratio between heads and tails is. Yes, late last year a new bit of maths dropped relating to if you flip a coin, keep track of if it's heads or tails, and you stop when there are more heads than tails. And let's say you do that over and over. And then you ask the question, hang on a second, if I stop whenever there are more heads than tails, what's the average ratio of all those sequences where I compare the number of heads to the number of tails? And there's going to be more heads than tails, but how many more? And if you calculate that and work it out, in general, it turns out, and yes, this is why it's a Pi Day video. And look, I'm as angry as you are. It's pi. It's pi on 4. If you flip a coin until there are more heads than tails, the ratio is pi on 4. So that's what we're going to do. This Pi Day, I'm going to calculate pi from my 10,000 coin flips, which has actually come together quite well. Previously, this Pi Day was going to be us calculating pi on the moon. You may have seen the update about that went out recently. Sadly, like a lot of space missions, it's been delayed, so we can't do that. That will be next Pi Day, hopefully. Previously, this should have been a Pi by hand year. I was going to try and break the record. Turns out that's going to take longer than I expected, so that's also delayed, but will happen. Link in the description if you want to sign up for updates. So what I'm going to do is basically go back to normal. I'm going to do a standard Pi by hand. But this time, instead of doing long, tedious working out by hand, I've previously flipped a coin 10,000 times by hand. And from that, we can extract a value of pi. And unbelievably, no one noticed that you get this value of pi on 4 from multiple coin flips until last year. And so I'm like, well, this is great, breaking news. So here's what we're going to do. I'm going to explain why you get pi when you flip a coin. Then we're going to get pi from flipping a coin. Let's do it. Right, I'm going to use these to represent a sequence of heads and tails. We can kind of arrange them across here. And actually, before we even start, we've got a pretty tight range on what the average ratio can be. Because the highest it can be is if, boom, straight out the gate, you flip a heads. You've now got more tails than heads, as required, and it's 100% heads. It's the highest possible ratio. Or we could have thousands of flips before eventually we have more heads than tails. And when that happens, it will have just, because there's so many, just gone over 50%. So really our range is 0.5 to 1. And because we're calculating pi on 4, it means we've already narrowed pi down to between 2 and 4, which, compared to some historic Pi Days, we're doing pretty good. Now, what if we didn't get heads straight away? What if the very first flip was tails? Well, now we're going to have to keep going. And the shortest sequence it could be now is 3 flips. It can't be 2, because the best case scenario is we get heads, right? But now it's 50-50. It has to be more. It has to be greater than 50%. So potentially another heads. So now that's the shortest sequence where it goes tails, heads, heads, stop. And that's I guess that's a half times a half times a half. That's a half cubed probability of happening. And the ratio is 2 out of 3. But what if we didn't get that second heads? The next shortest would be 5 flips. So for us to keep going in the first place, that would have to be tails there. Okay, and then the next one, well, it has to be 2 more heads, right? Because we need to get, it needs to be 3 out of 5 heads for us to stop after 5. So it would look like that. There it is. Okay, next shorter sequence is 5. It ends on when we flip this heads, and that's the one that tips us over to more heads than tails. So the probability of this sequence happening, half times a half times over, 5 of them, half to the power of 5, we can add that in. And the ratio is 3 out of 5. Great. So we've, oh, hang on. Wait a minute. Yeah, this one works, but so does this one. That's also a perfectly valid sequence. That's 5 long and would end at the same point exactly when we flip that one. So there's, I'll pick that up later. I can replace it. So there's 2 of them. Okay, so now for each run of coins, we need the probability, we need the ratio, and we need how many options there are. So we multiply this one by 2. Let's have a go at 7. Right, I've set us up 7 spots, and we're going to think about what sequences could possibly end at the 7th flip. And by end, it means that has to be us flipping ahead, because that's the point at which we have more heads than tails and we stop. And at no point before then can we have had more heads than tails, otherwise we would have stopped. Including the very first flip, that has to be a tails, otherwise we would have stopped on the heads. The second one could be heads or tails. We'll come back to that. Let's start by the case where we flip 3 tails first. So the tails are way out in front, and then heads come slamming back and they get it right at the end, because 4 out of 7 is the point at which this one means we've got more heads than tails. So that's 1. Write that down. However, this third tails here, that could happen later. We could have, that one was a heads and that one was a tails. That would work nicely. We can move it further, that's 2 if you're counting. We can move it down again. That could be heads, that could be the tails. We can't do it again, however, because if this was heads and that was tails, it doesn't work because we've already now, look at that, 2 tails, 3 heads, we would have stopped. So we only get those 2 extra ones. So now we're up to 3 altogether. Now, the other case was if that was a heads there. Now, if that's a heads, this one can't be heads because otherwise we'll have more heads than tails. It's got to be tails like that. And then that's still heads over there. And then these can go either way. This is either a heads then a tails, or it's a tails then a heads. Both of those work. You can't delay it any longer. So that's 5. If you want to pause and go through that yourself, you're very welcome to. I spent a long time in my notebook, which I'm pointing down here because I've still got all my, this was me trying to work it out the other night, and I got all these sketches of me going through being like, oh, what do I get in the sequence of heads and tails and tails and heads? There's me counting 5, and I was right, so I was able to fill that into the table. And the next one, we could do it for 9. There's 14 ways to do it. I didn't bother working that out. I put the sequence of 1, 2, 5 into the online encyclopedia of integer sequences, and it was all like, do you mean the Catalan numbers? And I was like, turns out I do. So why the Catalan numbers? Well, to get my head around it, I then drew a diagram, which I'm going to recreate for you very quickly here on my whiteboard, where I thought, you know what, let's represent on a kind of tree diagram. If you get a tails, you go down. If you get a heads, you go up. I had to roll that in around the dog, so it didn't hit the dog. And the goal is to end up above water. Very simple. So you start here on the surface, and then if your first flip is a heads, you're high and dry, you stop. If it's a tails, you're down here.
To clarify, when I mean above water, we stop flipping once we're 1 above this blue line. Because if tails moves us down and heads moves us up, being 1 above our starting point means we've now had more heads than tails.
And then I just expanded the tree diagram because the next one would bring you back up to the surface. This one would bring you even further below the surface. Then you've got a chance to get out here, heads, and there's only one way. That's one way to do that, there's one way to do that, but there are multiple ways. If you go up here next, or down there, and then up there, and then out, then if you count that, you're like, oh, actually there's 2 ways, because I could have gone all the way down and all the way back and out, or down, up, and out. And so if you start building up this diagram of all the ways you can flip heads and tails and all the places you can end up and all the times that you break the surface and escape, and then you've got to count the number of paths. You know what this is reminding me of? But if we flipped it over, it's Pascal's freaking triangle.
If you'd like to learn more about Pascal's triangle and the Catalan numbers, my friend Sophie McLean already has a fantastic number file video all about it. I highly recommend you check that out. And it works very neatly because Pascal triangle is effectively counting the number of ways you can get to any given point, and we can use the Catalan numbers to know when we cross over in the middle. It's really nice. Check out Sophie's video. But for our purposes, we're just going to use the fact that the Catalan numbers counts the number of possible head or tail sequences.
Right. Now we're going to put it all together. So we can take our table from before and put it into a generalized form. Catalan numbers start at n equals 0, the 0th Catalan number, which is 1. So we're going to use counting from 0. And the formula in general is going to be 1 over 2 to the power of 2n plus 1 multiplied by the nth Catalan number multiplied by n plus 1 over 2n plus 1. That's just what we had in the table, but now you put in whatever value of n and you get the next term in the series. And so we just want to sum these from n equals 0 up infinitely many of them. And then we get some result. And we do, I wrote down here last night, you can see there was my terrible attempt at that tree diagram. And over here next to it, I've written the formula for the Catalan numbers. 1 over n plus 1 multiplied by 2n, choose n. And you can put that in terms of factorials. We just substitute that in, and now we have one big chunky equation that gives us each of the terms from n equals 0 all the way up. We just got to work out how we turn that into pi. Okay, now we just need some kind of substitution or a way to rearrange this to get closer to pi. What's that noise? It's arcsine. It's the inverse function of sine that can be written as a series. Look at that, isn't that amazing? I mean, okay, look, here's the thing. I can't derive everything from first principles. It'd be a very long, and I'm aware of the things I'm about to say, boring video. So at some point, you've just got to take something on faith. And we're going to use the series expansion of arcsine. If you want to look up how it's done, you can. In fact, it involves binomials, and once again, Pascal's triangle. Lovely bit of mathematics. That's now your problem. All I'm saying is, doesn't that look similar? In fact, instead of arcsine of x, we could do arcsine of 1. Just put that in. Why not? And that means the x becomes 1, that whole thing vanishes, and it looks pretty much exactly like what we had before. In fact, it's just twice as big. It's 2 times whatever the average ratio of heads to tails is in our previous calculation. And what's the arcsine of 1? The inverse sine of 1. What value gives you 1 when you put it in sine? It's 90 degrees. It's pi on 2. So pi on 2 equals twice the average. The average is pi on 4. It's still making me angry. I mean, here's the thing. We're not surprised that if you flip a coin lots, the dogs come over to see why I'm getting emotional. We're not surprised that stopping lots of different length sequences of flips and adding them together gives us a series. That's what we'd anticipate. And we're not surprised that you can represent pi with an infinite series. That's classic pi. But I expect them to be separate things. What stuns me is that one of the series for pi happens to match a series for flipping a coin. It's ridiculous. I'm not happy about it. Thank goodness I got my therapy dog right here. Oh, who's a good dog? This ridiculous pi coin fact was discovered last year by a mathematician I know named James Prop, and James is going to put up a blog post for this Pi Day going through all the mathematics behind it. So I'll link to that below. You can check it out if you want to go through the detail. There's even a bit of calculus in there if you're into that kind of thing. But for me, normally, my problem would be, I'm like, oh, such a good fact. I need to do a thing for Pi Day. I could sit here and flip a coin over and over and over again and calculate pi by hand. But this time, I don't have to, because it turns out it's already been done by my longtime collaborator, Past Matt.
So here's why Past Matt was flipping a coin 10,000 times. I've had this long-running project in my career to calculate how thick a three-sided coin would have to be, which is a coin where it's equally likely to land heads, tails, or edge. And I've talked about this before. It's been on hold for a long time, but I found the current state of the art. But I realized the state of the art was a single paper. In fact, to this day, if you go to Wikipedia and look at the entry on coin flipping, the one citation for landing on edge is the paper Probability of a Tossed Coin Landing on Edge from 1993. So I thought I would recreate their experiments and I'll do my own experiment in an attempt to investigate that. Now, I never got around to analyzing the data. I did recreate their experiment by sliding the pound coin, which is what they used, off a horizontal surface 1,000 times. Then I did my own 10,000 flips. I'll link to it below if you want to have a look at the data. You can analyze it yourself. The big reveal, 14 times. Landed on its edge 14 times. Now, this whole experiment was a complete waste. It became a whole section in my book, Humble Pie. But the footage I never had a reason to use until now. Until I wanted to calculate pi.
So here's my big spreadsheet of data. I'll link to this below if you want to check it out for yourself. It's got the exact time I flipped every single coin. Wow, that was a late night. And then over here, started heads, landed heads, every single landing one. And that's just my kind of count if 14 edges. Good times. Now, we need to analyze this, which means we got to get it into Python. And I thought it might be fun to write the code. So all I'm doing here is I'm using OpenPyXL, that's Python for Excel files. I've set up the name of the file and everything. We want to count how many sequences we've been through, and that starts with 0 of them. I try to have remotely useful names. That's also 0. And then for each one, we need to count 2 things. How many heads and how many flips? What are we going to do with edges? Let's ignore them. Let's say they don't count. They don't count. It's got to be heads or tails, lowercase h or t. So what we'll do now is if the flip result equals heads, then we increment head count. So that goes up by 1. And then if flip result doesn't equal E, then that's our total number of flips. Okay, so all I've done there is each time we flip it, if it's heads, we add to the running head count. If it's not edge, we add to the running total number of flips count. Great. Now we got to check if we've hit the end of a sequence. So if that happens, we want to work out the ratio of heads to tails in that run. So we're going to say this ratio equals head count divided by flip count. I could do all this in one big long chunky line. I like to split things out because it makes my life a little easier to try and read it. So I'm going to take running ratio total, add on this ratio, and we've had one more sequence. So what do we call our sequence count? Count sequences. Well done, pass Matt. Always there for me. So we add 1 onto that. Now we want to reset because we're going to start another run. So flip count and head count now get set back to 0. Okay, that should be everything. Oh, I can't increment flip result. That's what it's flip count. What a dingus. Okay, that fixed. I kinda want to check it's working before we get the big result. Let's run it first without calculating the result. That's the big reveal. Each time we'll print the result, and then down here, we'll print what we think the ratio was. Okay, so now we can run it. It'll do that for all 10,000 flips, make sure it functions, and make sure it's doing what we expect. You never know with code. It's like if you just run it without making sure you've gone through to make sure everything's working properly, it's a very opaque process, which makes me nervous. Oh, there it is, it ran. Oh, these are long runs. Oh, okay, it is working. So that was a super long run. Look at it. And when it finally ended, it was just over a half. Next one was a head, so it was 1. Heads was 1. So this was a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 flips, of which 1, 2, 3, 4, 5, 6. So yeah, so it was 5 and 5, one more heads, tipped it over to 6 and 5, it stopped, and ratio of 54.54%. Okay, I'm happy the code is working. I'm gonna undo that one. Now, once it finishes running, let's just print. Should we do it all at once? Should we just print pi? Let's just print pi. You know what, let's do pi val equals running ratio total divided by count sequences. So that's the total of all the ratios divided by how many there are. That gives us the average. And then we multiply that by 4. And then we print pi val. So this is it, folks. This is the value of pi for Pi Day 2026. We're going to zoom. Let's get right in. I know that's messy, but I want a big number. Okay, ready? Okay, here we. What you can't see is producer Nicole is just out of shot over there. Very excited. Camera person Alex is over there, wildly indifferent. And now we run the code. 3.2266. That's better than I was braced for, because it converges so slow. Wow. 3.2266. For everyone who keeps a running record of my successes and failures, write that down. That's good stuff.
Obviously, while I was flipping a coin 10,000 times, I had a bit of fun, did some ridiculous bits to camera, and then I thought, you know what, why don't I try this in a fake collaboration where the coin unexpectedly keeps landing miraculously on its edge.
In a previous video, I said there was a trivial chance when you flip a coin of it landing on its edge. And even though you can balance a coin on its edge, it's a common misconception that that can happen when it's in motion. If you actually flip a real coin that lands on a physical surface, it will never land on its edge. And to prove why that's impossible, you need some very nice mathematics, some interesting physics, and some things you might not know. The first step, however, is just to actually flip a coin and take a close look at what happens. If you watch what actually happens when you what? Oh, come on. Okay.
All right.
Okay, about the collaboration. I got it, it landed on its edge.
No, you didn't.
No, seriously, I flipped it.
It's not possible.
First take, I landed on its edge.
No,
I know what we proved, but I'm just saying it happened.
Do it again.
There's no way. What?
You show me then.
See?
No.
Yes.
Way. No.
Yeah, I don't care what your physics says.
It can't happen.
I know, but I did it again and it's bang on the edge.
Entropy in the...
No, okay, you come at the worst time. It's ended on the edge.
Do you know what it's going?
I've got some terrible news about our collab.
I
You spent literally minutes.
Oh.
Oh.
I'll see you later. But the...
Yeah, Steve Mould and Tom Scott did stand around waiting for as long as it took for me to get that coin to land on an edge. Absolute legends. Sorry it took me 8 years to get it out, folks, but here we are. And now, back to Modern Matt for the final wrap-up.
And we're done! Oh, it's so great. 2026, literally 2-6 in the digits of pi. So write that down for the next 12 months. Pi equals 3.2266. Ah, fantastic. Now, some updates for the people who watch right to the end of the video. Yes, we will do pi by hand again. We've done some testing. We've got a new method. We've done a bunch of research. We've got a whole team on it. It's gonna take so many people for so long. I'm gonna need so many volunteers that are all prepared to sit there for a while, and we haven't really got a plan for that. We're trying to work out the best way to do it. If MoonPi is a success on the first launch, the leftover funding from that will go into Pi by hand, which means we can probably do it at the scale it requires. I promise I will give you at least 12 months warning if you want to come along and be part of the Pi by hand calculation. Link in the description for the sign up form. I will keep you in the loop and I will tell you more than a year in advance when we're going to attempt it. So don't panic, you will be there. Moon Pie, the update is out. That's a lot of fun. Go check it out. Link to it below. Hopefully we will launch at some point this year. We'll see what happens. And just in general, thanks for watching the videos. Oh my goodness, this is a wonderful tradition, calculating pi. And I couldn't have done it without Past Matt. Big thanks to Past Matt. Thanks to Sophie McLean for all things Catalan numbers, Jim Prop for discovering this ridiculous thing. I'll link his blog post, you should check that out. And of course, Steve Mold, Tom Scott for waiting for a ridiculous amount of time for a dumb joke that I didn't release for 8 years. That's a pretty accurate representation of what it's like to be friends with me. So that's it. Thanks for supporting the videos. Thanks for everyone on Patreon. You know, I feel like Pi Day is like end of 1 year. You know, you get like financial years and school years. I run on Pi years. So that was the end of the 2025-2026 Pi Day season. And now we're gonna go into the next one. And so that's it. So I guess we don't need this coin until next time. Oh no!